Welcome everyone to the SNAPP seminar. We are really excited today to have Andrea Montanari speak to us. And Andrea is a professor in the Department of Electrical Engineering at Stanford University. Oh, right. And we are recording, thanks for the reminder. So we are recording the meeting. So as a quick reminder, if you don't want to be recorded, there is a live stream on YouTube that you can watch. Okay, so I'll take a brief break to explain the logistics. So we encourage the participants to type your questions in the chat box, and basically we will have so Andrea has some of his collaborators who will answer questions on the chat box, but in addition, there'll be a short break for questions in the middle and a longer question and answer session at the end. All right, so we're really excited to have Andrea with us, and he has a long list of achievements and awards, so I'll just pick and highlight a few of them. So he was co-awarded the Sigmetrics Best Paper Award in 2008. He received the CNRS Bronze Medal for Theoretical Physics in 2006, the Okawa Foundation Research Grant in 2013, and the Applied Probability Best Publication Award in 2015. He is an Information Theory Society Distinguished Lecturer and has received the Information Theory Society Research and Teaching Award as well. And he was invited as a sectional speaker at the International Congress of Mathematicians and is an invited IMS Medallion Lecturer for the 2020 Bernoulli IMS World Congress. So we're really excited to hear Andrea tell us about self-induced regularization from linear regression to neural networks. So take it away. Thanks.
Okay. Thanks, Christina, and thanks to the other organizer, and thanks everybody for joining. Okay, so this will be about some recent progress on machine learning, let's say, or statistical learning, and a good part of this work is in collaboration with Song Mei, who was a student in my group and is now joining Berkeley, and Yi Chao Zhong, who is a PhD in my group, and they will be apparently online and answer question in chat. Okay, so the kind of problem we'll be talking about today is supervised learning. So to remind ourselves what is the setting, we have data that are IID samples from a common distribution, and these are come in pairs yi, xi, where yi is a real number, is a response. Think of it as the label of an image, and xi is a vector, a feature vector. Think of it as a vector representation of that image. And what we want to come up with from this data is a function f from Rd to R that enables me to predict new labels given the feature vector. And our objective is to minimize the prediction error on a new sample from the same distribution. So this is measured in terms of a loss function, L, and I'm interested in the expected value of this loss function. Okay, so this is the setting of statistical learning. This is, of course, a problem that has been studied for 50 years or more, and there is a classical and well-established theory or viewpoint on this problem that I can summarize in one slide, kind of oversimplifying a bit, but it is based on three ideas. The first idea is empirical risk minimization. So what you want to minimize is the expectation of the risk, the expectation of the loss on a new instance, on a new sample, okay, that is not on your training sample. So how do you do it? Well, you try to minimize the empirical risk. Since you don't know the distribution, you minimize instead the empirical average of the risk over your training sample, subject to the function belonging to a certain class F. Why do we hope this method to work? Well, one key idea is the one of uniform convergence. So the idea that, perhaps for n large, the empirical risk is close to the population risk or to the expected risk uniformly over all functions in the class F. And of course, there are many results in of this type, but here the important thing is that this error term goes down for a fixed class of function f, not too complicated, goes down as n goes to infinity. Okay, so if this holds, then minimizing the empirical risk is a good idea, perhaps. And finally, from a computational standpoint, how do you hope to minimize this empirical risk? Well, what we would teach students and writing papers until not long ago is that you should choose the cost function L, the loss function L, and the function class F. Of course, you won't parameterize your function class, and optimization depends on the parameterization, but you want to choose L and the parameterization so that the empirical risk minimization problem is convex. So if it is convex, then you can try to use all sorts of algorithm to minimize it. Okay, so this is the classical theory. Just one aside to remind us why do we want to constrain the function class. Notice that when I define the empirical risk minimization problem, I constrain the function to belong to some class script f. Why do we want to do that? Why don't we minimize over all possible function? Well, if we minimize over all possible function, we can end up with models with predictors that are really silly and would probably not generalize to unseen data. They fit perfectly your training data, but you don't generalize to test data. Okay, so now this is all very beautiful, and there is very beautiful math in it, and all sorts of interesting research questions. Unfortunately, since 2010, none of these three ideas seem to hold anymore, at least for some applications. Okay, I wrote for many, but depends on the point of view. These are many applications, most applications, some applications. And to give an example of why this does not hold anymore, one example to keep in mind is, of course, multi-layer neural networks. Okay, if you have never seen what this is, it doesn't really matter, but let me explain you. So a multi-layer neural network is a parametric class where the parameter theta is a sequence of matrices, W1, W2, WL, and the dimensions of these matrices are chosen so that I can multiply from left to right. Okay, and now the function is obtained by composing matrix vector multiplication and application of a nonlinear function sigma, where sigma applied to a vector applies the same function entry-wise to the entry of that vector. And standard examples that you might keep in mind are hyperbolic tangent, or this max x0 positive part, which is also known as the ReLU nonlinearity. Okay, so this is what is multi-layer neural network. So now let's see why the three pillars don't hold anymore. The first, of course, to go out of the window is convex optimization, right? Because even if I take the simplest possible loss function, the square loss, now this objective is completely non-convex, right? So I am really not following that. The second that goes out of the window is the uniform convergence, and at least seemingly, this is a paper by a group at Google Brain and Moritz Hart and Berrecht of a few years ago that demonstrated this very clearly. Here they train some standard state-of-the-art neural networks like Inception and AlexNet on again a standard image recognition data set. And what they observe is that when you fit it on true labels, okay, the training error quickly goes to 0. So you're perfectly fitting the data, and despite this, you achieve some 10 or 20% test error. Now, what's even more interesting is that you can replace the image labels, cat, mouse, dog, etc., by purely random labels. So this is the red curve in this plot, and what you see is that you will be able to fit to 0 training error also that artificial data set. So the function class that is encoded by multi-layer neural networks is rich enough that can interpolate data points, all the data points, even if these are pure noise. So it can interpolate white noise. And in particular, the train error will be 0, but the test error is possibly much larger than it. Okay, so the fact that you have small, the train error is not a good predictor for the test error. And this is, another demonstration of the same phenomenon, in which this is a paper by Misha Belkin and co-authors, in which they plot the test and training error as a function of the number of parameters in the network, and they see that the optimal performance is achieved in a regime in which the number of parameters is much larger than the data points, and the training error is 0. So the training error is 0 and the test error is positive. Okay. Okay, so this was for empirical, for a uniform convergence. You would say, okay, at least empirical risk minimization is still there, because after all, I'm minimizing a loss, right? Well, one has to be careful here, because what you're doing really is running some gradient descent or stochastic gradient descent procedure. This is, for instance, gradient descent. And this cost function that you're optimizing is highly non-convex. And we saw that it has at least one global optimum that is an interpolator, so it's 0 training error. Now you can easily understand that if there is one that has 0 training error, probably there is many, right? If there is a lot of parameters so that I can fit pure noise, I can fit it in many different ways. So there are many global optima. And so the global optimum that I select will depend on the initialization and on the details of the algorithm. So this means that when I tell you I'm minimizing the risk, I'm not telling the full story. I have to tell you, how do I initialize, how do I choose the step size, which algorithm do I choose, etc. And this was a point in particular that was very much developed and pushed by Natis, Rebro, and collaborators. All right, so this is the outline of the talk. So I'll try to give a big picture of some things that we think at the moment might be the way out of this conundrum, and then describe one key idea that I want to emphasize, this of self-induced regularization in a toy model, and then present results about infinite width neural network, that is kernel methods, random feature models, and neural tangent models. Okay, and I should mention at the outset that this is an area in which there is a lot of very smart people that have been working and doing very beautiful work over the last few years. And here I cite a few papers that in particular influenced me, by Misha Belkin, Sasha Racklin, Peter Bartlett, and others. So unlike this work here, one difference is that we will focus on some simple neural networks, and we will obtain some sharp asymptotics in what is known as the lazy regime, or equivalents for some random feature models. Okay. So before going in the technicalities, I want to describe the big picture. Okay, so moving back to what I said before, the classical view is that you do learning by empirical risk minimization, you make it tractable by using convex optimization, and you obtain low generalization error by regularizing your cost, or by imposing the complexity of the cost function, right? So by this I mean, for instance, you minimize this plus some norm of theta. This is standard way that you see in the textbooks to do this. Okay, so in this neural network work, okay, convexity goes out of the window, but what is believed now, or one thing that is believed to be part of the solution of the puzzle, is that despite being non-convex, the problem becomes tractable because it's very over-parameterized. So there is so many global optimum that very likely your random initialization is close to a global optimum, so you can just carry gradient descent through and achieve it. So this is what, this is my picture of the set of global, so this is RP, and imagine P to be very large, 1 million, but I cannot draw. And this blue line is the manifold of points that achieve zero empirical risk, right? So this is the manifold of networks, so that fxi theta is equal to yi for each I less than n. So this is the set of pure interpolators, right? And this is perhaps your initialization. So this is a high dimensional manifold, and this is your initialization theta 0. And this small red arrow is the path of gradient descent. Okay? So this is the picture I have in mind. You have this, manifold that is all, everywhere. And so if you initialize at random, you are close to a point in this manifold. And if you run gradient descent, you quickly converge to it. So this is our parameterization. Of course, the algorithm will select which specific point on this manifold you get and its property. So, there is, it's not just about minimizing the risk, but there is an algorithmic mechanism that selects one minimizer. And finally, you don't regularize by adding a penalty in the cost, but I will argue that there is a kind of self-induced regularization that emerges because of the nonlinearity of the problem. And I'll try to explain this in the following. Okay, so just the setting of this talk will be that we focus on 2 layers neural networks. So this is, or one hidden layer. So this is this class of functions that are parameterized by a vector of real numbers and then by this WI, first layer weights. So if you want to draw a picture of this, you will draw so something like this. You have x1 to xd. So these are the coordinates of the output. And then there are 1 to capital N will be the intermediate layer nodes, and then I don't find these diagrams particularly useful, but okay, I find this more useful. And okay, one interesting remark about this class of function and pretty much any other model in this world is that it's preserved by scaling. So if a function is a neural network and I rescale it by a real number, the resulting function is also a neural network. Okay, trivial observation, but this trivial observation brings about something interesting, that is this lazy regime. Imagine now taking a random, a random or an arbitrary initialization A0, W0, and look at the neighborhood of this random initialization. So linearized around this point, okay? So I'll put an epsilon to say that my movement from this point is very small, and I can put in 1 over epsilon in front that is perfectly fine because my class is scale invariant. So I can, rescale it any way I want. And now I do Taylor expansion. And if I do Taylor expansion, okay, this is first order Taylor expansion. The 0th order term has a 1 over epsilon, but the first order term has no 1 over epsilon. And now I can compute derivatives, okay? And if you compute derivatives, the derivative with respect, the gradient with respect to A, and the second layer weight takes this form. And the gradient with respect to the W's takes this form, where here there is a typo, this should be sigma prime. All right? This is just, taking derivative of 2 layers neural networks. Okay. So, this kind of idea was very much, developed or clarified in a paper put forward in a paper by Jacob, Gabriel, and Hongler. And the way I'm deriving it as a completely general phenomenon is really due to Shizai and Bach. Okay. Now, one interesting thing is that there are initialization A0 and W0 in which this thing is negligible because different neurons cancel each other. Imagine of taking the second layer weight to be plus and minus 1 and to cancel each other. So I can choose the initialization in such a way that this is 0. In any case, this is not a very interesting thing because it doesn't have any parameter. A0 and W0 are fixed numbers. So the real interesting meat is this one. Okay. So in that regime, what you have is that the neural network is the sum of two terms. And these are linearly parameterized classes of functions because they are parameterized here by the AI and here by the BI. Okay? So I'll call this the random feature class and the neural tangent class. Okay, so the random feature class is simply a 2 layers neural network in which the W's are fixed and I train only the AI. And the neural tangent class instead is something slightly, okay, here again there is this typo, this should be sigma prime, in which I take sigma prime and then I multiply by this function ai.x and I always fit the AI. Now, sometimes in the literature you will see called the neural tangent class as the sum of these two. I prefer this definition because in any way, when you sum the two, the second one dominates because it has much more parameters. And now we choose an initialization, and throughout the talk, I'll fix this initialization WIs to be IID and uniform in the sphere, over the sphere. Okay, so this is basically the two models that I'll be talking about, the random feature and the neural tangent model. And again, the way one should think about them is that they are approximation of the neural network when you train the neural network in a special way, as to be in this lazy regime. So you have to scale weights in a suitable way. And there is a bunch of papers that shows that if you do that, then it's well approximated by RF and NT. Okay, let me pause 1 second, 1 minute, and see whether there is any question about the setting. Or half a minute.
Just feel free to just unmute yourself as well.
Okay, if the setting is clear, it better be clear because otherwise you miss a lot. Okay, there is another part of the setting is how do I do training? I'll do something very simple. I'll do ridge regression. What is ridge regression? I have these parameters A, so I'll minimize the sum of square residuals and then minimize with the L2 norm of the square residuals. And why I want to do this? Well, I'll be particularly interested in the limit of this as lambda goes to 0. This is the regularization free method. And the reason why I'm looking at this special training method is what I was describing here, right? This picture is that when I start training, I'm probably very close to an interpolator. So locally, what I'm, if you zoom up this looks like a line, and you are converging like this, right? And what does it mean that it looks like a line? It means that your function fx theta is really a linear function, and since I'm taking the square loss, the risk is locally a parabola. And now if you minimize a parabola with some degenerate direction, you converge to the point that is closest in L2 distance. Right? This is standard for Clore fact. Okay, so this is said again, if you do gradient descent with respect to the empirical square loss, for instance, in the overparameterized regime, the limit of gradient descent is equal to the ridgeless limit of ridge regression. And there is actually a closer correspondence between the two trajectories as well. Okay, so I want to start with a toy model to explain the key idea, one key idea that I want to emphasize later. And okay, what toy model? Linear regression, of course. Okay, so let me step back for a moment and say that as before I have data that I will encode in a vector y and the matrix n by d x. And I do just plain linear regression. I'll just put a ridge regularization. Oh, here I should have called this beta. Sorry, this is beta. So this is just doesn't have anything to do with neural network. Is the simplest, one of the simplest learning methods you might use, and of course it has an explicit formula. And it depends on the empirical covariance of the data, that is x transpose x divided by n. Now let me add a twist to this picture. And the twist, I think that the first paper that studied, not that studied this, because this is studied as noisy invariable model, but pointed out this phenomenon is this one by Kobach et al. And the twist is the following: I take my covariates, my feature vector, and I add Gaussian noise. See. Okay, and now I do regression with respect to this noisy covariate. And again, I have the same formula as before, except that I replace sigma of the covariance of x by the covariance of z. What happens now? Well, it's crucial to look at, the important thing is to look at what happens at the covariance of z. What is covariance of z? If I expand z, I write z as x plus alpha g, where g is a Gaussian matrix, you obtain this. And now you see this piece has zero expectation. This piece has zero expectation. And this piece has expectation that is proportional to the identity. So I might hope that this covariance is similar to this. So what does this mean? It means that when I do a ridge regression with the noisy covariates, this covariance matrix is equal to the original covariance matrix plus a piece proportional to the identity. And again, if I neglect the G piece here, you obtain that this estimator is similar to the estimator in the model in which there is no noise, but in which I increase the regularization by alpha square. Okay, so what is the punchline here? And this could be computed in much more detail, of course, but the punchline is quite easy. That adding noise to the covariates is a little bit like adding a ridge regularization. No, very simple remark. Now, what I want to argue is that if you take one of these high-dimensional models, that are nonlinear in the covariates, like the random feature model or the neural tangent model, and you put no regularization, except that you're looking at the mean norm interpolator, this produces an effective regularization. It's equivalent to fitting a simpler model with an effective positive regularization. In other words, the role of covariates noise in the simple example that I described before is played now by the nonlinearity in the functions. Okay, let me try to go there now and start with the first case, that is the infinite width limit, to set the stage mostly. And okay, it's interesting to look. Okay, there are many things that are interesting to understand here, but one interesting thing to understand here is that this model has, a connection, and in fact is that we are trying to fit, is equivalent to a kernel ridge regression method. So this is the way I described our, the kind of estimator that we are trying to study for these two function classes, right? Parameterized by the AI here and the AI there. Okay. Now this can be equivalently looked at as a problem in which I'm minimizing this objective over all functions, and I'm penalizing over I'm penalizing a certain norm of the function, and the norm induced. So before I had the norm of the coefficients, so the norm induced by the norm of the coefficient in function space is the RKHS norm associated with these two kernels. Okay, so this is an RKHS norm, the producing kernel in Hilbert space. Okay, so there is a way to define this norm in such a way that, and this is nothing mysterious, right? You have f at is a linear function of A, so the L2 norm here translates in another Hilbert norm on F. Okay. Now, what happens when n goes to infinity? You see, the form of this kernel is that they are empirical averages of something. So as n goes to infinity, you can hope that this converges to the expected kernel, and this kernel also converges to the expected kernel. Okay. Now, using this, I can study. It's not too difficult to study the prediction performances, the generalization performances. So here I take, as a setting for the data, model for the data, I assume a very simple model in which the data are, of course, IID, as I said before, and then the xi are uniform on the sphere of radius square root of d, or sometimes will be Gaussian. And the response is a function applied to the data plus epsilon. Nice. Okay. And so here again, I'm looking at two layers networks in this lazy regime, if you want, with capital N equal to infinity, and this is the network width. Okay. And so a quite simple picture arises here, and is the following: for any integer, if you assume the sample size to be, bigger than d to the L and smaller than d to the L plus 1, then the risk of this kernel-rich regression method, that is equivalent to this thing, is the projection of the target function onto polynomials of degrees bigger than L plus small o stuff. Okay, and no kernel method can do better than this. So what's happening here is the number of data points is of order d to the L. That is basically the number of degrees of freedom in a degree L polynomial. And kernel-rich regression fits perfectly degree L polynomials and doesn't treat as noise everything that is of degree L plus 1 or larger. Now, one thing that I want to emphasize here in this result is that this holds for any lambda between 0 and the maximum value. In reality, okay, so what this means? It means that you achieve optimal error at lambda equals 0. At lambda equals 0, you have no regularization, so you're really minimizing yi minus f hat of xi, plus 0 times norm of f hat. So you are interpolating the data, because of course the kernel class is big enough that you can interpolate any finite set of data points. So this is one case in which the optimal error is achieved by interpolants. Okay, so now this sets the stage, because what we know now is that as long as the number of data points is much smaller than this square, I will only be able to fit linear functions basically with this kind of models. So perhaps I should stop a minute at this point to see if there is any question. Okay. If there is no question, but please interrupt me if you have. I'll move to the random feature model. I mean, to study now the finite width random feature model. So here the number of parameters, or the width, is n. So we have now a real model with n neurons and parameters and lowercase n sample. And again, as I pointed out before, the number of degrees of freedom in the target function, f star, if f star is a polynomial of degree L, is d to the L. Okay, so because of this, I'll focus on this proportional regime in which the number of data points is proportional to the dimension. So basically, I'm trying to fit a linear function, and the number of neurons is also proportional to the dimension. All right, and more precisely, I'll take the tree number go to infinity in such a way that capital N over D goes to a number psi1, and lowercase on N over D goes over function to a constant psi2. Okay, and it's useful to decompose my target function into a linear part and a nonlinear part because I hope to do well on the linear part and not well on the nonlinear part. And these are the two norms of the two components. Okay, so in this model and in this regime, we can get a precise characterization of the risk, and this is given by a theorem like this. You take your activation function and you decompose it into a linear and nonlinear part, and the decomposition is according to L2 of the standard Gaussian measure, and the only dependence on the activation function is through this ratio of the linear to the nonlinear part. And under this setting, the risk is given asymptotically by the sum of two terms, a bias term and a variance term. And you recognize that this is a bias term or a signal term because it's proportional to the linear norm of the linear part of the signal. And this is a variance term because it's proportional to the noise level. Again, data here comes with noise. And the epsilon I has a variance 2 square. And this B and V, script B and V, are completely explicit function that depends on the ratio psi1, psi2, and on the form factor of the activation function, zeta. So this thing is telling you that basically you're not fitting anything of the nonlinear part. No? And these functions are completely explicit and they're given by some such formula. And okay, I will not ask you to parse this formula, but only to show that, you know, it's just a matter of solving these two equations. These are two equations, U1 and U2. They give rise to a fourth order algebraic equation in one of the two variables, and you substitute the solutions in these three polynomials, and this gives the risk and the variance. So, okay, it's difficult to parse, but it's straightforward to evaluate on MATLAB. The math that is behind this is really random matrix theory for kernel linear product random matrix. That is a subject that is less studied than standard random matrix theory, but for which we begin to have some tools. And in particular, we build on work by Cheng and Singer. And rather than the formula, it might be useful to understand what this formula means. Okay, so one way to interpret the formula is through this noisy linear feature model. And okay, this is the following model. Our model for the data is the following. Oh, here there is a typo. This is A times U. Okay, so what I'm fitting is something that is linear in the hidden units that I'm calling U. Okay, this is the random feature models. And what is the linear units are obtained in this way. Okay, applying my activation function to W times X. And I can decompose this into a linear and a nonlinear part. And for simplicity, I assume that the constant part is 0. Now, this is a decomposition, orthogonal decomposition in L2. So this means that these two terms are uncorrelated. And it also means that, okay, so you might think of replacing this piece, the nonlinear piece, by just random variables that are uncorrelated from the axis. And they have the right variance. So I multiply here by coefficient sigma star to keep the variance right, and I call Zij just standard Gaussian random variable. So this noise linear feature model is a model that is Gaussian. So I replaced the U by the U tilde and correlated. Okay, but it's a model very similar to the toy model that I described before, because I have feature vectors, covariate vectors, and then noise added to them. And one way to interpret the theorem that I described before is that in this proportional asymptotics, then the two models, the nonlinear feature models and the noisy linear feature model, are asymptotically equivalent in the sense of having the same risk. Okay, so in this case, if you want, we can prove explicitly that what's happening here is that the nonlinearity is playing the role of noise in the covariates, and therefore is regularizing the objective. Okay, so we can compare this kind of the prediction of randometrics theory that I gave before, the explicit formula that I gave before, to simulations, and they match very well. And in particular, we see this phenomenon in which, so the line here, this prediction and data points are simulation. We see this phenomenon in which the minimum error is achieved at very large over parameterization, and there is a peak when, so this is plotted, the risk plotted as a function of capital N over N. So again, this is the number of parameter, and this is the number of samples. So 1 is the interpolation threshold, the threshold at which there is as many parameters as data points. And so if you plot the training error goes down and touches 0 here and 0 after that. And this is the test error that has this thing. If you turn on regularization, this divergence disappear, but depending on the size of the regularization, there is a peak. Now, I want to spend a few minutes to describe a few insights that come out of this explicit formula that we have for this model. First thing is that, okay, as I pointed out before, the optimal error is achieved at infinite over parameterization. So N goes to infinity. So very wide networks. Second point is that if you turn on some regularization, as I showed you, this so this kind of pattern in which the error goes down, up, and then down again has been called double descent. As I say often, I don't think this is a good name because it doesn't emphasize the most interesting part of the model. And this is a way to see it, is that if you turn on some regularization, this peak here disappears completely. In particular, the optimal regularization is given by the lower envelopes of this curve and this monotone decreasing, perfectly noisy, monotone decreasing. A more interesting fact is that the optimal error is at capital N to infinity, and that this is achieved with lambda equals 0. So this demonstrates this picture in which I plot the error as a function of lambda for various aspect ratio for various value of n, and you see that the optimal error is achieved here, that is at lambda equals 0. Now, one interesting fact is that this depends on the level of SNR. At high SNR, this is the case. The minimum is at 0 regularization. At low SNR, instead, the minimum is at a positive regularization. And finally, let me emphasize once more the effect of nonlinearity as a ridge regularization. And here I'll use the formula for capital N over D going to infinity. So very wide limit, but this extends to the moderate size limit. Here, what I plot is the bias and the variance predicted by our theorem as a function of the regularization parameter and the nonlinearity parameter. So zeta2 is the nonlinearity parameter of the activation function. And you see that these are the level lines, and you see this effect in which, increasing lambda, so regularizing more, has the same effect as decreasing zeta. So increasing lambda is exactly the same effect as increasing the nonlinearity. Okay, so increasing the nonlinearity in your activation function that is going down in this direction regularizes your model. And this you can make it perfectly formal. If you look at the formula for the bias and the variance here, they are not a function of the regularization parameter by themselves, but they are a function of the regularization parameter plus psi2 inverse divided by the nonlinearity. Okay, so the way the regularization enters is this one, so nonlinearity trades off with regularization. Okay, so now all of these are kind of simpler models. Now look at a more complicated model that is most closely related to neural network in the lazy regime, that is the neural tangent model. So in this case, again, my function takes this form where my parameters are AI, and here, of course, I made a mistake. The AIs are vectors in RD. Okay, so this is this funny thing in which I first pass them through the sigma prime, multiply by x, and then I multiply by AI times x. And the W are random, but I fit over the AI. Now, the most important things that changes here, the single most important thing, is that I have a model with n neurons, but n times d parameters, okay? Because each AI is a vector of length d. And the number of samples instead is still lowercase n, okay? So the interesting trade-off between number of, so this is true both for the neural network and for its neural tangent approximation, right? So this is an important thing. So the interesting, trade-off that will emerge is how big is lowercase n over with respect to n times d. While before in the random feature model, if you remember, in the random feature model, we were studying n proportional to d and lowercase n proportional to d. This is an okay regime, but it's not the most interesting regime for the neural tangent model, because this corresponds, this guy corresponds to number of parameters much bigger than number of samples, quadratic in the number of samples, while we would be interested in number of parameters of the same order or slightly bigger than the number of samples. So because of this, we will look at this kind of regimes in which the three parameters go, the three dimension go to zero, the number of neurons is, in fact, log d to the c is big enough, but let me write is the same, d to the epsilon for some epsilon positive, and then the number of neurons is less than a constant times d for some constant. So let's say n is less than 1000 times d. Okay. Now, let's be honest. While this assumption, I don't think this assumption is strong. It's not common that you take, number of neurons, that is more than 1000 number of dimension. But this assumption is still it's an interesting overt problem to try to relax. Okay, so this assumption we put in here for conceptual reasons in the proof, and it will be interesting to get rid of it. But still, it captures an interesting regime. Okay, so first theorem. So now what we compare is number of parameters and number of samples, and it's no longer completely obvious that if you have as many parameters as number of samples, you can interpolate the data. It's still a system of linear equations, but it's a system of a linear equation with a messy random matrix, right? The interpolation question, f of xi theta equal, or a equal yi for all I, can be written as a system of linear equation, phi times a equal y. And the question is it true or not that when phi is rectangular, this system has a solution? In other words, is it true or not that this matrix phi has full row rank? The matrix phi is whatever comes from the mapping of the AI to f at the sample points. Okay. And this theorem proves that, yeah, indeed, it's basically true that if you have, nd much larger than n, and here we have an extra logarithmic factor, then this matrix has full low rank and an NT interpolator exists with high probability. I should mention that this is a question that has this kind of, this is sometimes the question of capacity or memorization capacity of a neural network, is a question that has been around since the 70s, since Stonecover, and recently in the case of, this neural tangent model, 2 layers neural network and neural tangent model, there have been, papers by Danieli and Bubek and Mikulincer, that give related result. One difference is that they don't get exact interpolation, they get interpolation up to a small error. Now, the more interesting fact about this result is that the way we prove it is that we prove that this matrix phi, the matrix phi is again the matrix that give me the vector of fitted value at the sample point. This matrix phi is full rank, and to prove it, we really, what we do is that we analyze, of course, the kernel matrix that is phi transpose, that takes this form. All right, so this is an interesting random matrix. It's random because of the W's that are uniform on the sphere and the X's that are Gaussian. And we obtain a characterization of the minimum eigenvalue of the matrix that takes this form. Basically says that the minimum eigenvalue is bigger than this V of sigma plus small o of 1, where V of sigma is the variance of sigma prime, where G is Gaussian. And in fact, it tells you a bit more, and this bit more implies that basically this lower bound is tight. Okay, so the minimum eigenvalue is of this order. Okay, so now you see what's happening. Remember this noise in feature model, noise, the first noise in covariance model, the toy model. What our heuristic argument there was that the covariance of the noisy variables was equal to the covariance of the real variable plus a coefficient to the identity. And here something similar is happening where, you know, the nonlinearity in sigma is adding a piece proportional to the identity in the kernel matrix. Right. So because of that, we can, you know, thanks to this technical result, we can characterize the generalization error. And the way I state this is in terms of an effective linear model. And this effective linear model is again the same that I described before, in which I do linear regression with a ridge penalty. Okay. Okay, needless to say, this effective linear model is very well understood. Just to make the point here, I write down what is the risk asymptotically in the proportional regime for this linear model. Okay, so if I take n and go into infinity to delta, then I guess this risk for ridge, this is the risk of ridge regression in the proportional regime. This is standard random matrix theory. Okay, so the theorem here goes like this. Okay, we assume that the number of samples is at least a constant times d, and okay, this is not really an assumption, because if you have less than d samples, oh, I should write something important instead. We assume that the truth here is linear. Okay, and you assume that you have at least d samples, which is perfectly reasonable, since if you have less than d samples, you cannot learn this d parameter in beta 0. Okay, and okay, the expectation of sigma prime is different from 0, and this important parameter that gives you the variance of sigma prime. Then the following happens if you are above the interpolation threshold. Okay, so n the number of parameters much bigger than the number of samples, up to a logarithmic factor, then the risk of the neural tangent model is equal to the risk of linear regression, linear ridge regression that I described before. I'm regressing with respect to the raw features, where the regularization parameter lambda is replaced by this effective regularization parameter, that gamma f, which is lambda plus v divided by the expectation of sigma prime square. In particular, even if I have lambda equals 0, so I put no regularization in the original method, I do min norm interpolation, I get something that is equivalent to linear regression with a positive gamma. Okay? So this is what I kind of anticipated that I would get to, that the nonlinearity in the neural network is effectively producing a sort of ridge regularization in the effective model. And okay, this you can check in data. This is plotting the test error as a function of the number of neurons and comparing the neural tangent kernel ridge regression, so the neural tangent model, with the linear ridge regression. So linear ridge regression is just this plain ridge regression with respect to linear features. And what happens is that, you, for instance, if you look at these curves that are the dark blue curves, here the neural tangent model has lambda equals 0, and the linear model has gamma equal 1. Okay, this is exactly what we predict from the theory, that you should tune the regularization of the linear model, and the two curves match when the number of neurons is large enough. Okay, and this is another way of plotting the curves as a function of n, and we plot them also against the overall prediction that comes from random matrix theory. Okay, so this is one figure to summarize my intuition of these models now, is that what's happening in these high-dimensional nonlinear models trained in this lazy regime is that the model is rich enough to interpolate the data, and it will interpolate the data, but something that can happen in high dimension is that a function can stay almost linear, for instance, linear almost everywhere essentially, but can be deformed in a smooth way as to interpolate any number of data points. So in high dimension, something can be extremely smooth. It can be almost everywhere linear, or almost everywhere quadratic, whatever, and then interpolate all the points. And what's happening is that the model, there is this self-induced regularization that is such that the function learned is linear, or is as complex as it needs to be given the number of data points, but then is deformed to go through all the others. Okay? And we have now several examples of this phenomenon. Okay, so this is what I mentioned several times. The big difference is that, okay, this gives a rich set of models in which it's clear why you don't need to trade carefully between model complexity and sample size using a regularization parameter, but there is an actual inbuilt regularization mechanism. Let me mention a few open problems. Here we focused on square loss, but it would be very interesting to look at the other loss, in particular classification losses. We have some partial results on max margin classification, but there are some, actually there are a lot of open questions there. So if you read this paper, you'll find several open questions. Here we looked at this very simple data distribution, which data is basically spherically symmetric. In reality, real data are not spherical symmetric. If you followed closely, you will have noticed that the results that we have for the random feature models are sharper than the results that we have for NT models. So it would be interesting to fill that gap. Yeah, in general, even for the random feature models, we have pretty much the complete picture only in this proportional regime and proportional to D. But for other polynomial scalings, we don't have the complete picture. I gave you some results, but we don't have the precise picture everywhere. Okay, that's all. Thank you.
Thank you, Andrea, for a great talk. And we'll take some questions now. There are some questions in the chat box, so I'll go perhaps first in order of
I don't.
In there. I'm guessing, Bin Nguyen, that your question was already answered by Song. So Tong Xin, if you want to unmute yourself and ask your question, feel free to do it now.
Sure. So thanks for a great talk. So in the earlier part of the talk, there was this very beautiful picture showing why optimization works for ERM. That you have the global minimum is basically a manifold that's pretty widely spread in the space. So if you start randomly at some point, you will be able to get there, right? So how do the results you presented connect with this picture, or how far are we from getting to this one, right? So how far are we how are we getting there?
Okay, so first of all, I have a slides in which I have at least 20 papers that get results of this type. But okay, so one way to get this picture is that, if you remember, I described this this lazy regime in which I tune down epsilon, right? So I have the model 1 over epsilon f of x, okay, whatever. I don't know where it is now. Yeah. Now, this formula, if I take epsilon small, this is correct. I mean, you have to bound the remainder, but it's no. So this means what? That if I train the model by taking epsilon small enough, as soon as there is a solution in the, let's say, in the empty model, there is a solution in a solution of bounded norm in the empty model, there is a solution close to the initialization in the actual neural network model. So, there exists epsilon. So if it's nothing, right? So you have a nonlinear map. So you have a map F that from real P to reals to the n, right? This maps all the parameters to the value of the parameters in the function. And what you have to solve is, or let me call it phi, or let me call it capital F. And what we want to solve is f of a equal y. All right? Now this function also depends on a parameter epsilon. And as epsilon goes to 0, this function becomes m times a plus order epsilon. So as soon as m is full rank, equal y, sorry. As soon as m is full rank, there exists an epsilon such that the original nonlinear system has a solution. This is just analysis. So this means that our result implies the following, that this picture is correct. So there exists an epsilon for any nd bigger than n times log factor. There exists an epsilon positive such that this picture is correct. Now, in the paper, we don't try to compute what is this epsilon. I think will be an inverse polynomial function, but we don't try to compute it. So this means that this picture is correct as soon as you pass the interpolation threshold. Now, most other papers instead focus on this kind of setting where really epsilon basically scale in a predefined way, something like 1 over square root of n or 1 over square root of d. Okay, okay, they obtain various results depending on ND, but no one gets this tight results. So the best one, I think, is Oimak and Soltano Kotabi, but it doesn't get to this one. I think they require n bigger than n or something like that. So it's wrong by a factor 2 in the exponent. Okay. Now, I think it would be interesting to understand what is, really precisely the trade-off between epsilon and the over parameterization ratio. Yeah, I mean, it's an interesting question.
I see. Thank you. So you have shown us many papers. So exactly which one describe this, explain this phenomenon, or like,
This is
or
the paper on the NT model.
okay, thank you. Good. Great, thank you.
I mean, this remark here is a side remark in that paper.
Hi, thanks for the wonderful talk. I was wondering if you could explain a little bit about the universality of the results based on the random matrices. Are they, how flexible is this on different kinds of random matrices? Are there other tractable solutions?
Oh, good question. I mean, it's a very interesting question to explore. I mean, I would guess that there is some degrees of universality. For instance, this result, I would guess there is quite some degrees of universality, the usual universality classes of random matrices, namely. So here, what is your random matrix that you want to analyze, really? I mean, the one basic building blocks that you have to start with is analyzing this type of random matrix, right? Sigma of x times w, xi times wj. Okay, so take this matrix over I less than n and j less than capital N, and then rectangular matrix. This is basically the design matrix. If I do this regression problem, this is, you know, in the random feature model, this is the design matrix. So I'm trying to solve basically this problem, right? So you want to analyze the singular values of this matrix. This is a bit, and you know, more than that, but you know, this is the basic step. Now, there are results of universality of this by Do and Wu, I think, but I don't remember exactly. But I would assume that if you take, again, we take here x that is Gaussian, but if I would assume that if I take x that are IID component, for instance, with some moment condition, and W that have IID component, then the spectrum remains the same, right? Mm-hmm. And you know, probably similar. Now, what would be interesting is to understand what happens when these things are anisotropic, right? So you wouldn't expect really that X is a IID component unit covariance. So an interesting model would be that you take the W is up to you to decide them. So it's really the initialization of your network. So take W to be the standard initialization or uniform on the sphere, that doesn't really matter. And then take Xi to be normal 0 sigma. You know, so you have some covariance that, you know, the standard setting of random matrix theory, for instance, that, you know, the empirical spectral distribution of the covariance converges to some limit that is, you know, bounded support. And then, you know, repeat this analysis. Right? So now that could be interesting. I mean, that there I expect things to change a little bit, right?
I see. Thank you.
So I would, you know, as opposed to universality, I would try to look for, you know, where things change, right? I imagine that if you take sigma highly anisotropic, then, you know, some of the scalings start to change.
Thank you very much.
Hello. Hi. Thank you for the talk. I find it very interesting. So I have a questions on the slides of the test zero versus the SNR. Can you switch to that slide? It's around 50, slide 50, something like that.
50. Okay, you tell me.
Like slide 47. So because I saw that when SNR is greater than 1 and when SNR is less than 1, there is like two very different function shapes. The slide 47.
47.
Yes,
Okay.
47. Sorry.
Now I don't know how to see because this is. This one?
I cannot see.
Wait. It froze my. Let's see. Okay, so I have to
No
do
problem.
this. Okay, can you see it now?
Yes, this, yeah, the next one, I think not, is inside 3, yes. So I'm not sure why there is the test zero is like having two very different functional shape between SNR equal to 5 and SNR equal to 1/10.
Well, okay, again, first of all, what is really, what would you expect here naively, right? Naively, you would expect that as the noise level increases, you have to regularize more and more, right? So this is the risk error as a function of lambda for various values of error parameterization, and you can focus on the lower envelope of these curves that also coincide with large over parameterization. So this is the dash curve. So what you expect naively is that as you have more and more noise, you have to regularize more and more, right? So this is minimized at some lambda, and you would expect that this lambda increases with the SNR. Okay. Now, what is surprising here, what happens here is that increases, right? Here the minimum is at 0. Here the minimum is at a positive value, right? So it's increasing with the SNR. Now, what is surprising here is that it's really not very small for high SNR. It increases with lowering SNR. It's not as very small for high SNR. It's exactly 0. Okay? And what is the explanation for this? Well, the explanation, you can understand it already in the toy model that I described before. Since that there is some self-induced regularization that comes because of the nonlinearity, there is already some non-zero lambda that comes. It's built in the model, in other words. It's built in the model because the activation function is nonlinear. So if you add a little bit more of regularizer, that doesn't improve over that. So as a function of the regularization parameter, this is constant. Or in other words, in this example that I was showing before, you see what's happening is that this bias and risk depends on lambda plus 1 over psi 2, right? So there is a non-zero effective regularization even if I put lambda equals 0. A non-zero self-induced regularization even if I put lambda equal to 0. Okay, so this is why the optimal lambda stays to 0 for a while. Yeah, okay, that's the best that I can.
Okay, thank you.
Hi, Andrea. Nice talk. This is Teng Yuan Liang.
Hi, thank you.
Hi, Andrea. I have two short conceptual questions. One is for random nonlinear model. If the sample size scales with, let's say, polynomial of the dimension, and you show that this model is very much like if you expand the lower degree component plus the higher degree nonlinearity itself amounts to a certain implicit regularization. It's like adding independent. And you show the equivalence between these two models. My question is there precise asymptotics in this polynomial regime on the like a low degree component plus IID noise type of model, the precise height characterization on that risk, or the same, or even if it's dimension scale with sample size but anisotropic? To what extent do you think random matrix theory is able to provide sharp?
So okay, just to understand to figure out whether I understand what you are saying. So you are saying take a model in which my feature vector phi are basically, okay, how do I write it?
Sigma XW.
Let's say phi. Oh, okay. Let me call them. Okay, let me write something. Q of xi plus wi, where Q is from RD to R D less than equal than L. That is, Q is the mapping that Q of X is the mapping that puts all the moment mapping X1, XD, X1 square, XD square, X1, X2, blah, 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 Xn minus 1, Xn, XD minus 1, XD, etc. Right? So you could study this model. You remember the model that I was looking at before was Zi is Xi plus W. I think that, and then I do linear regression in the Xi, or I do linear regression in the Zi's, right? Another model that one could try to study is the following, in which the Zi are, Q is the mapping that takes a point in RD and maps it into the evaluation of the first, all the polynomials of degree less than L, less or equal than L on that point, right? And then you add noise to this covariates, right? That could be an interesting model. And then I do regression with respect to Zi, right? Now a question is, do I know how to do random matrix theory for this model?
In the regime when n, let's say, is
yeah. So now you take n equal d, n is equal to gamma or psi times d to the L. Yeah, I would assume, okay, I don't think it's out there, but I would assume that it can be done, right? I mean, it doesn't seem, but yeah, I mean, it's an interesting research project. I mean, I don't think it's an easy consequence of anything. I don't think it's an easy consequence of anything.
Thank you, Andrea. And another short question is, so in reality, we have just a sample size at dimension, right? We are building some version of asymptotic, either let's say n divided by d is a constant, or let's say n is some constant times d squared. In reality, we just have one pair. Which asymptotics you feel are, I know there's no universal answer, but which one in your experience can be more accurately predicting the finite sample performance? Because for any pair of n and d, you can sort of it as n divided by d is a very large constant.
Yeah, well, good question. Well, I think that it really depends on the specific application, right? And now, I think that in many of these computer vision that people look in machine learning, well, probably this proportional thing, especially when you use a deep network, so the number of parameters is effectively very large. I don't think that that dimension proportional to number of parameters, for instance, is necessarily the best thing. But I don't think either that dimension fixed is a good thing. I think that probably, proportional. I mean, both of them are useful, right? But I would bet that probably, a proportional thing with a small exponent is a good idea, right? Perhaps number of parameters quadratic in the number of. But again, then the question is that all of these models are limited in the sense that the data distribution is very simple, right? So all of these notions are a little bit fuzzy.
Thank you, Andrea. Nice talk.
Thank you.
Thanks, Andrea. I think we're going to stop the recording right now. But if anyone wants to continue and stay and ask a couple more questions, you're welcome to.